All right, so what we're going to do is we're going to describe camera link, and we're going to start at the very basics, the very specifics of how the data gets over, how to use a camera with camera link. So what is camera link? Camera link is a protocol for sending camera data from the camera to the PC. And you'll have a camera link camera because it has a fairly specific, unique connector that you don't see on a daily basis. This camera is not necessarily unique, but the camera link cables are themselves. They are 26 pins, and inside is a pair of 13 LVDS pairs for high signal integrity. The two types of connectors they can be are MDR or SDR, the SDR being slightly smaller. There is a standard for sending data over these lines as well, this power over a camera link, but most cameras have a other connector for power. And there's also a 14 variation called light, but that is very often not used. So when it comes to camera link, one thing that's kind of confusing is there might be two camera link ports on a camera. And what that means is this camera doesn't have two outputs, but it has more bandwidth. So your camera link configurations can use two cables to increase the bandwidth. So we have our chart over here, the configurations. Light and base use one cable with a max bit rate of 10 to 24. This bit rate depends on what kind of image data you're sending out. And then medium full and this 80-bit mode use two cables and have a max rate of 48, 64, and 80. When you're looking at the camera, you specifically have some of the other configurations your camera you might have to consider are the color palette it sends out. So mono 8 to 16-bit, RGB if it's 24 to 36-bit. As we just talked about, the base, medium, full, the 80 or light mode, the camera clock speed that it's actually coming out, and another thing you got to be worried about is this thing called tap configuration. And the tap configuration is the actual format that your computer or your camera is sending out. So in this case, it's a 1 pixel scan left to right. Here it's a 2 pixel scan vertically, or scan 2 rows at a time. And there are multiple different ways of weird configurations of how the camera is actually sending the data. And if you don't have the proper configuration in your frame grabber to support this, then you are not going to be able to capture the data. So along with knowing the full parameters of your camera, you got to find a frame grabber that can support all those different types of configurations. So your frame grabber is the device you connect to your PC to grab the frames from your camera and use on your computer. They're almost all PCI cards you slot in. They'll have 1 to 2 camera link connectors. Even if it has 2 connectors, make sure it supports full or 80-bit mode if you need it. Some frame grabbers with 2 connectors on them will support 2 cameras. So it'll be, say, base plus medium or full. So picking the right frame grabber that can support the right bit rate, the right number of connectors, the proper clock rate with the proper configuration is all very important. So there's a lot of information about camera link in here, but why would anyone use camera link? And it comes primarily down to when it was created. It was created in early 2000, so there wasn't many options then. So this was really a protocol designed for high bandwidth in the early 2000s. Not only that though, there also is a big benefit is camera link is the distance. since these signals are very signal resistant, they can go quite a long distance. And with the amount of different kind of configurations, you can get high bandwidth. Full has up to 8.5 gigabits, which is 680 megabytes, which is a lot of bandwidth. And the configuration options for the camera user allowed for a lot of different cameras to send all these different kind of configurations. So it made the sender side of the camera simpler to design. So, and just for comparison, USB, is the go-to thing nowadays. But back in early 2000, we're talking about, more than 10x or decrease in bandwidth, and even potentially even slightly less distance. So it wasn't even until USB 3.1 in 2013 where we actually got the amount of bandwidth we could compete with. Even then, it can't compete with distance, even though they can still get fiber optics. And even with these two nowadays, USB is a shared communication channel. So, it wouldn't be as reliable as having a connection where this entire bandwidth is reserved for the specific camera. Even today, it's quite impressive how much bandwidth you can get across to these cameras. All right, so now I'll show you some cameras, or I'll show you some camera link equipment, and we'll go from there. All right, let's move that over. So I got a camera link connector here. So we have the MDR and SDR. So, and this is one specific cable. It's very common for your camera potentially to have an MDR, but most frame grabbers use the SDR because it slots better into your PCI cards. So these cables are bidirectional, so it doesn't matter which end you put them in, they will both work. That is not always the case. Some cables are specifically designed to be directional. So this is the end you'd plug into your computer, and this is the end that you plug into your camera. I'll go over this why in a little bit, but basically it comes down to the internals not being the same, basically. So in base configuration, there are slower signals that don't need to be shielded. So these guys right here, these are all unshielded pairs, while we have data lines here which need to be high resilience, so they are shielded, so they won't be disturbed as much. So these cables are only designed to be used in base cameras, or with things designed for base. They will not work for things that are full. So here we have a frame grabber. So we have two connections here, and on the back they'll be labeled base, medium, and full. And sometimes frame grabbers will have an external thing here for other sorts of triggers if your camera needs them, but that's pretty unique. Right here is a camera link camera. So here we have an external power supply and a weird one, or a power plug, and down here we have our camera link connector. Okay, so what is in base? What we have is we have a shield, which is usually just grounded to the shield itself. We have our data lines, X0 to X3. We have our X clock. We have this thing called CERT TC and CERT TFG. So this stands for serial to camera, and this one stands for serial to frame grabber. And these are your serial UART style lines. They're going around like 57600, nothing too fast usually. And then we have our CC lines, and these are command control lines, and for like things for like triggers and syncs. And these are usually just GPIO lines. And what you can see here is these lines have minuses, then pluses, and that is because, like I said before, these are LVDS lines, and LVDS lines are differential. So this pair creates the data for x0, this pair creates the data for x1. So this differentialness allows the signal to be constructed because the interference will affect both wires and they can cancel out each other and make the signal easier to read on the other end. So now that's base. So we can see that base right here. So we can see the control lines and the x0 to x3 data lines. The other two common modes are medium and full. And as you can see, this is connection 1 and connection 2. So medium uses the first part of the camera link connector, and then full uses the second part of the camera link connector. So before I said the directional camera cables, basically they would not work here because those unshielded pairs wouldn't have the signal integrity to allow the data to go through. Why this slicing of the second channel is even a thing is based to the design of the chips around it. So camera link is built around these chips called channel link, and they have a certain size to them. So in base, we need one chip, we have one connector. Medium, we need two chips, and we have the two cables. And then in full, we have three chips. And what this actually looks like from a diagram perspective is you have these channel link chips, which basically take in parallel data, serialize it into a channel link signal, and on the other end they'll have a deserializer, and then it pumps it back into standard parallel data. And these come in 28 or 21 flavors. Camera link only deals with the 28 version, and the thing to note is it gets 28 bits per clock, and that means it takes 7 bits per clock, and that's quite a odd number. So what that means is on the rising edge, 4 bits of data, 4 groups of 4 get clocked in. And then on the falling edge, 4 groups of 3 get clocked in. So basically we have a 4-3 clock. And why that is the case is, my speculation is that this format fits a pretty good use case of sending 888-bit data in a pretty compact format, which is 24 bits, and it allows for 4 bits of other signals to also be there. And what that could be used for is not only cameras but displays. So channel link, these channel link chips were the groundwork not only for camera link, but they were also the groundwork for this thing called FPD link and flat link, which were both display protocols for driving screens before embedded DisplayPort. The 24-bit, this channel link serial data gets converted back into this 24-bit data, where it will also get clocked in with the F-sync and L-sync like a normal display. Now, in the camera link world, we call these FVal, LVal, DVal for frame valid, line valid, data valid, and then we have one spare that doesn't get used. What this looks like in practice is once val goes low, that's the start of the frame, but nothing's getting clocked in. Nothing's getting clocked in. The LVal goes low, still nothing's getting clocked in. It's not until all these plus dval is low that the pixels will actually start getting clocked in. And once this goes high, the pixels stop. Once this line goes high, this is line 1, it's triggered in and it's good. And now we're on line 2, and we can grab the line data pixel here, clocks up. Once again, these pixels won't be grabbed. Then we can get pixels, and then once these rise, the line ends and the frame ends. So in this made up example, We grabbed like 3 pixels per line for 2 lines for a frame. Now, some things don't respect dval and just respect lval, but that's a per frame grabber kind of thing. All right, so this part is going to be quite in depth, and we're going to basically map the pixels to bits on the specific LVDS lines for camera link. We're going to look back at this graph. We have our data lines, the LVDS lines for data, X0, X3, Y0, Y3, Z0, Z3. Now, these are the physical lines, but they map to the documentation, these ports, A, B, C. Each port is 8 bits. We have 3 ports, 8 bits, so that's 24 data lines. And then we have our control signals up here. So you'll see a bunch of 8 bits, and I'm assuming that's 8 bits is a nice character length. So I think that's why they grouped up all these data lines into 8-bit chunks. Next thing, we take a format. So in 8-bit, A0 through A7, these are the pixel values mapped to A0, A7 on the port. Now that's a nice 1-to-1, but when you go to 10 bits, A0 maps still to A0, but A9 will map to B1. So this B doesn't necessarily have to map with the corresponding B values. Same with A to A. And they not necessarily will go in order. So the C0 goes to B1, but B4 goes to B8. So this can kind of be confusing when you do your mappings and stuff like that. But we're going to do 10 bits, 10 bits, 1 pixel. So we're going to do A0 through A9. So that's A0 through B1. Okay. Now we take that port number. So we have these A0s, and then they go over here. So this is the specific bit position in the sequence over the 4 lines. So B1 goes to RX8, A0 goes to RX0. Now this is the actual bit sequence in one clock of data. All right. So every clocked piece of data will send out this specific sequence of values. So now what we have to do is we take this chart, we map this over to the ports, which maps over to the RX signals, which gets sent out to here. So our 10-bit 1-by-1 tap looks something like this. So we have A1 to A4, A5, A7, A8, A9, A6, then our devals, fvals, lvals, and the spare value. So that's how kind of the mapping went. We took these A values that map to these A through B ports, which map to these RX bit sequence, which map to the 4 data lines like this. So some of the keen among you might have noticed that full only had 2 ports on it. So that's why full equaled 64 bits and not 72. So what some people did was they wanted to maximize the amount of bytes. So they grabbed all the unused bits and they put it into this special 80 bits mode. So it's like the full mode, but utilizing every unused thing. So these are the 2 charts. So we can see in the base, medium, full, and we can see that these chunk here are not being used. And the other thing that they reuse is they got the spares, and they don't use devals anymore. And they only use 1 frame valid. So when you add all those chunks up, what you get is 16 bits more of data. So if you take our 64 plus 16, that's how you get the 80 bits output. That's if you need true maximum bandwidth over CameraLink. One piece of history that might be helpful on your journey through CameraLink is knowing that National Semiconductor is the company who created the standard. Now, Texas Instruments acquired or merged with National Instruments in 2011. So at that point, Texas Instrument took over the creation of making all the special channeling chips and those types of things. So if you see in the documentation with our national semiconductors in it, that's why. All right, and now we're gonna try showing you some cameras. So the cameras we're gonna look at are these AndyMech 1000M. They've got one camera link, so they're base, and they've got this wonky power cable. So these are relatively cheap cameras. They're not even CMOS, they're CCD, which stands for Charge Coupled Device sensors. Right here, there's just like a little mounting thing, so you can actually screw in different lenses. So without that, you can actually see what the actual image sensor looks like. So, yeah, so we're gonna go basically hook this up and see what it looks like on the camera link side. So what we're gonna start doing is actually capturing some images from this. So I'll walk you through FrameLink Express software that ImperiX uses. So most everything you want is in this top nav bar. So we have camera 1, camera 2, so you can switch between them. You can see this little camera goes away because it doesn't detect it. So if we go back, so this actually starts the feed. So you can see here data is coming through, but our timing is not correctly set up. So what we're gonna do is we're gonna skip to this guy here. And what I like to do is if you don't know exactly what the settings are, you go to this learn, and it will figure out based on the timings it's receiving, it's logging the information. You can press OK and then hit apply. Now you can see that the image starts to look better. So currently this is a very dark image. So if I added some light, it will slightly come up a little better. We'll make this a little brighter. But what we're seeing right now is basically my hand, because this is a big lens on there. Okay. So if we keep going down the line, we have these to control when there's these things called CC pins, and they usually are set for triggering things. We don't have that on, we're not setting that up on this camera currently. RGBs, capture settings, don't care. This guy's really cool, so you can see what the statistics are. So we're going at our frame rate of like 30 frames, and our clock is 40 megahertz. Very cool. Well, the last one is this. So you can see basically a histogram of where the data is. Most of it's really dark until I put my hand, which reflects some of the light. The other thing you can do is you can zoom in specifically, so you can see the exact pixel value. All right, so now what I want to do is I want to actually increase the gain of this. So we're going to pull up the terminal, and I'm also going to pull up this PDF. So in this PDF, you can see that it's set to 57,600 baud, stop bit of 1, data bit of 8. So just make sure we have that. And then the other thing is, unlike normal serial data that has like a new line or a return, carriage return or something like that to determine when the packet ends, this one actually uses specific hex bytes. So you can see start of message is 64 decimal and end of message is 13 decimal. So that's what this little guy over here is for. So I've got some commands to make my life easier. So I grab this over here, put it in hex mode. In the ASCII, you can see what it looks like. So this is gain adjustment of 4, so it's a 4x gain. Let's put it back into hex and send. Now you can see it's so much lighter, so you can really see my porous skin a lot better. We also have ways to change the pixel depths. So that's what this guy does. So this is, I don't know what the command stands for, but the 12 is for raw 12. So you can press send. Now it's all crumb, because now we're trying to display 12-bit data in 8-bit form. So that's what all this banding is for. So what we're going to do is we're going to hit 12-bit. Now it's going to be nice and back to normal. So yeah. So that's just a quick example of how to use Camera Link camera in the real life. And that's about it.